Hello and welcome back. We're going to be talking about specific heat capacity in this mini lecture. Now, whenever you have something warming or cooling, we want to use this equation. Now, we've seen with heat how we can have something warm up or cool down, and the heat involved in this change can be calculated from this convenient equation. And like I said, I call it the warming equation, but it could be something cooling down or warming up. Now, the heat involved depends on the mass of the substance, okay? A larger amount of material will involve a larger amount of heat to have that change in temperature. And the heat also depends on something called the heat capacity or the specific heat capacity, all right? Now, the heat capacity is how a material responds to heat that you put into it. Some materials increase in temperature very little when heat is put into them, while other materials increase in temperature a lot, okay? So let's just jump in and do a practice problem here. This is from the Open Stax chemistry textbook, and this will give you an idea how to work the numbers. And this is a typical warming cooling problem where we want to use the Q equals mc delta T equation. So our first step is to calculate the change in temperature. Whenever you see that little delta symbol or the triangle symbol, that means final minus initial, okay? So if you ever do this and you get a negative number, that's completely fine because negative signs, as we will see, indicate a direction of heat flow, all right? So here we just plug in the final temperature minus the initial temperature, and we get 1,510 degrees Celsius, a very big number for this iron block, okay, or this piece of iron anyway. Now, what we want to do next is to plug these values into the warming equation, okay? So Q equals mc delta T, and we plug them all in, and we get a value of around 50,000. So notice how the grams and the Celsius cancel, okay? So we were left with just capital J, and remember that stands for joules, a unit of energy, okay? And we, of course, round this off to 3 sig figs. Now, the last part of this problem involves converting calories to joules. This conversion factor should be at the bottom of your conversion table I have provided to all of you. If not, please write it down somewhere so you can easily reference it, okay? So 1 calorie is equal to 4.184 joules. And so our final answer here is 1.21 times 10 to the 4th calories. Okay, so you should use dimensional analysis to show the conversion because it's hard to remember if you should multiply by 4.185 or divide by 4.185, okay? And the final answer again has 3 sig figs because every value in this word problem has 3 sig figs. We've got 75.0, 0.449 joules, and remember the delta T was 1,510, which is 4 sig figs, okay? All right, let's do another problem. So pause this video and take time to read it and perhaps even sketch out how you would solve it. Here we want to calculate the specific heat, which is the little c in the warming equation, all right? So let's write out Q equals mc delta T. This is the warming equation in case you still haven't memorized it. And we solve for c by dividing both sides by m delta T. And so what we want to do now is to plug in our temperatures. But wait, we have 2 temperatures, right? So once again, we have to calculate delta T before proceeding onwards. So delta T, remember, is final minus initial. And so be careful when you decide which temperature is the final and which is the initial. Once again, it's completely normal and okay to get a negative number for the delta T, all right? And so here in this case, it's a positive value of 66.4 degrees Celsius. Now that we have the change in temperature, we can plug things in to find the heat capacity. After you get all the values with units in their places, you can get your calculator and determine the value. Now notice here that none of the units cancel because C has very complicated units. On my calculator, I get 0.711, and the units are joules per gram per degree Celsius, okay? Now what is this substance? We're supposed to look at table 5.1 in the Open Stax chemistry textbook, and if you look at the very bottom, it might be hard to see on the screen. We see silicon has a specific heat capacity of 0.712. That matches pretty close. So this could be the identity of the substance, all right? Now, let's talk about water. First of all, we have this definition of the calorie, and I like to use calories a lot to even though it's an English unit. Okay, so the amount of heat needed to raise 1 gram of water 1 degree Celsius is 1 calorie. And so what does that mean? Well, we saw Q equals mc delta T, and heat or Q or energy is 1 calorie, and that's equal to 1 gram times the specific heat capacity of water, which is 1, times the change in temperature, which is 1 degree Celsius. So if we're warming from 50 to 51, that difference is 1 degree Celsius, and so it's 1 calorie. So notice that the heat capacity for H2O is 1 calorie per gram per degree Celsius. So you should, of course, memorize C equals 1 for water. That's the definition of the calorie, okay? So let's look at an example here. How many kilocalories is involved when 100 grams of water cools down from 50 degrees Celsius to 22.5 degrees Celsius? So once again, please calculate delta T if you're given two temperatures, all right? And so it's the final temperature, which is 22.5, minus the initial temperature was 50. Okay, let's look at that carefully here. We get a negative number, and that's okay, all right? Because we're taking the final temperature and we're subtracting the bigger 50 degrees Celsius number. So we get negative 27.5 degrees Celsius. Keep that negative sign in all your work as you move onwards. The next step is to calculate the Q, which is again mc delta T. Plug it all in. 100 grams of water. The heat capacity is 1. Memorize that, please. And the delta T is a negative 27.5 degrees Celsius. When you punch all this into your calculator, you get negative 2,750 calories. Now, what I want to do here is to convert this to kilocalories, okay? The problem should have said kilocalories. I think I mistyped something on these subsequent slides. So we divide by 1,000 to get kilocalories, and the final step here is to round it off to 3 sig figs, okay? 3 sig figs, because the temperature is 3 sig figs when you calculate delta T, and the grams of water is 3 sig figs. We will see later how a negative number just means that heat is released by the reaction or released by the hot cup of water to the surroundings. So it's okay to have a negative sign in your final calculation for heat. All right. Thanks for watching. Please like, consider subscribing. Have a great day, everybody.